to the bar. So this particular extension twist coupling has been quite well known. In fact, over the earlier time when they were modeling this particular effect, many people looked at it as a linear effect. There is a linear part to it, so that there's nothing wrong with that. But there is a large nonlinear part as well, and if you don't consider the nonlinear part, lots of things which come as a consequence of this trapeze effect will not be captured in your theory, and we shall go into some specifics later on. But one such aspect is, for example, torsional buckling, which of course happens when this axial load is compressive instead of being tensile, as in this particular case. So this trapeze effect primarily is a nonlinear extension twist coupling, and this is something which is more commonly observed in open cross-section beams with thin walls. So whereas this is for closed cross-section beams with thin walls, here it is open cross-section beams which are thin, typically like I sections, channel section, C section, etc. Now, why these are important is that these kinds of beams are very commonly used in engineering. Of course, we know a lot of aerospace applications of it, but there are non-aerospace applications as well. Again, in space, you see that they are used, for example, in trusses and many space structures where you have these closed cross-section beams, typically circular, sometimes elliptic, depending on the particular loading ratios. And then in antenna legs or radar legs, for example, then in submarine hulls, cooling towers, especially in power plants, the shafts which are used there, they are typically of closed cross-section, which are thin-walled. And then risers in offshore structures where you have oil drilling, for example. So there you would see many components of those offshore structures employ very commonly circular thin-walled cross-section long structures. Medical tubing, again, though this is not a typical beam that you would think of, again it has a very similar geometry to what we talk about here, and once again the same kind of effect, the brazier effect, the nonlinear bending effect will be observed there. Again, lots of sports applications these days are using these, like fishing rods, ski poles, etc. Here also you will find thin closed cross sections, and once again this effect becomes important if you want to analyze their behaviors accurately. Coming to the trapeze effect, this is obviously important where both extension and twist are there, and where the cross section of the one-dimensional structure is an open section. So some examples of those are, for example, rotating structures. We have been discussing over and again the helicopter rotor blades. So helicopter rotor blades, especially the flex beam part which is in the yoke, and or the entire helicopter rotor blade itself, including the airfoil cross section that you have. This can be considered as an open cross section beam with thin walls, because typically the airfoil cross sections which are used there are not very thick, so the thickness to maximum thickness to chord ratios are of the order of 10% at the most, which basically means that they are in this particular category. Then you have propellers, again because of the same reason, that they are rotating structures and therefore centrifugal forces are in place, and centrifugal forces are tensile as far as the beam is concerned. So that automatically comes into picture. Again, because of the aerodynamic loads and or certain control loads, you will have torsion coming in as well. So obviously there is extension and torsion in these problems, and the geometry suits our definition as well. Again, turbo machinery blades, not only the compressor and turbine blades that are used in aircraft engines, but other turbo machines commonly used in mechanical engineering as well. And again, in all of these situations, the commonality is the fact that they are all rotating, and therefore large centrifugal forces, which are axial loads, are present. So now we'll go into each one of them in a little more detail. First of all, the brazier effect, which is basically, as I said, a nonlinear moment versus curvature relationship in thin-walled closed cross-section beams, and presenting certain results based on some of our past work. And one such demonstration is for a composite, and again, as I said, both these nonlinear examples that I introduced in the previous slide are things that are present even in isotropic beams. but because we are primarily focusing on composites here in this course, I am giving examples related to composites. So, for example, in composites, you see if the ply layup is just 0 degrees alone, in other words, it's a unidirectional laminate. This is 0 degrees, 8 plies, and that's the entire thing. And then you basically see that the bending moment versus curvature initially starts off almost as a straight line, and then it curves around, and you cannot take moments beyond a certain value, and that is the limit moment that we were talking about earlier. Similarly, if you change the layup, again it changes quantitatively but not qualitatively. Once again, you see that it reaches a particular maximum moment that it can take, beyond which the curvature dramatically increases irrespective of the layup that you're looking at. Again, there's another layup over here, slightly different from this. So, in other words, the ordering of the plies will also matter. Just the difference between these two, for example, is that here you have the outer plies as plus or minus 45. Here you have the outer plies as 0 degrees, and you know that in bending, the outer plies are play a much more critical role because they contribute more to the bending stiffness being farther away from the neutral axis, and therefore you see a much larger moment that it is capable of taking. So that's basically what you see over there. So similarly, again, there are various other theories which were theories before this particular asymptotically correct theory was presented, and most of them were giving more conservative results. In other words, predicting this maximum moment load to be much lesser than what the asymptotic theory eventually predicted it to be. So in that sense, it was a safer design if it were used for design. But basically the idea is that we now have asymptotically correct theory, which though numerical results are presented for specific layups here, you have closed form analytical solutions for any arbitrary layup as well. You just need to plug in the actual angles for that particular layup, and then you can basically make this plot of the bending moment versus the curvature. So the geometry is basically like this. You have a thin walled circular tube, and you are applying bending moments at both these ends, and because of which the original circular cross section that you have starts flattening out, and eventually the limit moment instability takes place as is shown in this particular discretized picture there. Now let's go in a little more step-by-step fashion. So in this cross section we are introducing two coordinates, Cartesian coordinates x2 and x3. x1 along the length of the beam, and again this is something we will do irrespective of what type of cross section it is. So this kinematics you have seen earlier, you have done a part of it in the exam as well. Now you have a bending moment, let us say, which is applied to this. Actually it's a load which anywhere inside happens to be the resultant, happens to be the reactive resultant, happens to be the bending moment. So that's equal to m2, and that's about the x2 direction over here. So when that has happened, when there is no load, you have a circular cross section. When there is a small load, in other words, there is the initial curvature, the curvature is also small, there is no initial curvature, this is a straight prismatic circular cross section beam. And then when there is a small initial curvature, then you see that there is a small amount of flattening which takes place. Once you start increasing that curvature beyond that limit for that particular material and or geometric layup, then you basically see that there is a kink which basically forms, and that's when the instability actually happens. This is the initial stage, and then eventually it starts going rapidly. But one interesting thing to observe is that when you actually apply to real life structures, this is not the only failure that is there for this particular structure with this particular loading. It can so happen, for example, that the material fails, or it could so happen that there could be local instabilities which arise, because remember that the top portion is under tension whereas the bottom portion is under compression. So there can be local buckling which can be taking place, which is not what this is. So this is different from local buckling. This is something which is happening at the much more macro scale instability that we are talking about. So these are different aspects of failure, and depending upon the actual material that you have, in this case it is graphite epoxy, and the actual layup that you have, what is the thickness and what is the ratio of that thickness to the radius, and again what is the ratio of the radius to the length, depending on, and the moment itself, of course. Depending on all these, you will have a possibility that either this limit moment instability might come earlier than the other modes of failure that we discussed, or those might occur prior to this. Irrespective of what it is the nonlinear behavior, because most of these failures, even if it's material failure and or local buckling, etc., will typically happen in this particular range, and there the nonlinear behavior becomes very important. So if you don't take this nonlinear behavior into account, even the prediction of the other modes of failure like the material failure and or local buckling can be erroneous. So in that sense, not only for the prediction of the limit moment instability itself, which in some cases could be just a theoretical value if the other failure has happened prior to that, but to predict even that other failure, the nonlinear behavior has to be taken into account appropriately in order to predict its value more accurately. So first of all, what happens is, in a mathematical sense, you are applying a load because of which there is a bending moment, and that is about the x2 direction over here. When that happens, you end up, the primary result that you end up with is the curvature about the 2 direction. Of course, in a linear isotropic prismatic beam, it just becomes M2 by EI2. It's a little more complex when you have more couplings. You'll have other kinds of deformation combined as well. And as you keep increasing M2, your kappa 2 will increase. That is this curvature about the x2 direction. And when the curvature increases, obviously there is this in-plane warping which is taking place. Pardon for this particular picture, it's put in the other way, whereas these are in this particular way. Here x2 is horizontal, x3 is vertical, whereas here x2 is horizontal and x3 is vertical over here, or rather the other way around. So you see that this is the flattening direction that is basically indicated over here. And again, the asymptotically correct result will not only give you the bending moment versus the curvature relationship, it will also tell you the actual geometrical change which is happening on the cross section, because that is the warping, and you have closed form analytical solutions for the warping as well. So depending upon the value of the bending moment, you can actually plot the new shape of the cross section, which is non-circular, of course. So you basically see that, and this is what is an example of in-plane warping. Again, we've been talking about warping, remember, as a 3-dimensional field. So in other words, it has 3 components, W1, W2, W3, along the x1, x2 and x3 directions respectively. What is along x1 direction, which is along the beam reference line, is what we call as the out-of-plane warping, because the plane section no longer remains plane, it basically warps. So, and that is what is typically considered by most people, especially when looking at torsion of non-circular cross sections. But what we are looking at here is an example, classic example of in-plane warping. Another classic example of in-plane warping that we already discussed is when you just have an axial load, and the Poisson's effect can be a case where you see that the cross sections dimensions change in both the directions, and that's again an in-plane warping. But the in-plane warping here is much more dramatic, and you basically see that the ovalization, so-called ovalization of a circular cross-section. So that's the in-plane warping, and as you keep increasing your kappa 2, your in-plane warping also keeps on increasing. And this cross-sectional ovalization eventually leads to a drop in the bending stiffness so substantially that basically the limit moment is reached. But basically you can very easily see how this bending stiffness decreases, because you see that the bending stiffness that I have to calculate is about this axis, because the fact that earlier the cross section was here and it is slowly coming closer, and that basically decreases the moment of inertia about the x2 axis, and that's the reason why your EI2 effective will basically come down. And that which in turn means that your bending curvature is going to increase further. Okay, already it's the increase in curvature which caused this, and this in turn causes a further increase in curvature, and this kind of a loop eventually reaches a state where the curvature cannot be controlled, and that's the situation where you end up with the limit moment instability. But much before that also you basically see there's a nonlinear behavior between the bending moment and the curvature.
So which one is the 2-axis or AE2?
In all these pictures, the horizontal axis is 2 and vertical axis is 3. But this picture alone, here this is x2 and this is basically x3. Okay, so I'm sorry. So this is x2, the vertical is x2, and this is x3, because the bending moment is basically applied like this about the x3 direction, because of which the flattening basically takes place. So you can think of this pipe, and basically I'm applying the bending moment like this. So it is bending in this particular direction, and because of that there's a flattening which is happening in this particular direction. It's just a rotated form of these pictures. Any other questions on the Brazier effect?
So unlike any other theories, in the first place it will be like it gives this linear relations, right sir? Later on this curvature and this m by ei, m2 by ei2, that will be a nonlinear relationship between them, right sir?
See, basically any nonlinear relationship basically means that you can have an initial linear approximation to it. In other words, the relationship is always nonlinear, just that the nonlinear terms are very small compared to the linear terms when the curvatures are very low. As the curvatures become larger and larger, the nonlinear terms importance becomes more and more, and that's why you actually see quantitatively that they create an effect. But it's not that the nonlinearity is not there. It is qualitatively present, but quantitatively it is negligible. Okay, next let's go through a similar analysis for the trapeze effect. So this is the trapeze apparatus that I was talking about, and here as I said, it's nonlinear extension twist coupling, and this is something which is very common in thin open cross-section beams and also strips. Okay, by which we mean thin rectangular cross sections and or thin airfoil cross sections, for example. So here's a typical such thin rectangular strip, and another cross section which is like a cruciform. Again, an I section or Z section, hat section, all of these channels will all qualify under this category. And in all these cases, whether it's an open cross section or you have a thin rectangular strip, it's very easy to see that in all these situations the torsional stiffness is very low, because of which even with small values of torque, you're going to have large twists, okay, twists per unit length. But the specific interest in this particular case is what happens to the relationship between the twist and the extension. And the reason why extension is important in this case is the weight of the trapeze artist. And in this case, where it could be a helicopter flex beam or any turbo machinery rotor blade, it basically is the centrifugal force acts as the tensile load. Under those situations, how is the twist behavior? Now it's very easy to see that any open section beam that you take, for that matter the simplest case in terms of analyzing the geometry, a thin strip like this, if I try to twist this, it's going to be quite easy to twist. But if I apply an axial load which is tensile and then I try to twist it, it becomes a little more difficult. Okay, to make it a more down-to-earth explanation, more for a layman kind of an explanation, and in fact these were the kinds of explanations which were offered earlier on when the trapeze effect was first discovered, is to just consider this whole beam to be made up of a lot of fibers parallel to the length of this particular beam, and then you see that if the fibers were taut, that basically they are just left as it is, then you basically see that it's much easier to twist it. But once you apply a tensile load and make those fibers to be having a pre-tension, then you see that it becomes more difficult for it to be twisted. So same thing you can very easily observed through a very simple experiments performed on this particular apparatus as well. So in terms of the mathematics and then the numerical results which goes into it, for example, in such a situation, for example, when you have, again, in an isotrope, I said that both these effects are present in an isotropic beam, but in an isotropic beam, you need some initial twist in order to basically observe this particular effect as far as the linear part is concerned. But the nonlinear part, that is the nonlinear coupling between extension and twist, will be present even when there is no pre-twist. But again, we are taking an example of a composite in this particular case. There are some experimental results which are shown by these circles, squares and triangles over here, all performed on the same kind of layup, which is basically an anti-symmetric layup. And for that anti-symmetric layup, we are basically exerting a tensile load using an UTS specimen, UTS machine for example, but allowing the ends to rotate with respect to each other and being able to measure those twist angles between the two ends and therefore be able to get the twist per unit length along the length of the beam. So we are plotting that elastic twist angle at the tip, that is with respect to of one end with respect to the other, versus the axial force, and you see that this is the actual plot, this is the actual behavior, and which agrees pretty well with the experimental result. And then you basically see that this is a linear approximation to it. This is an example of some of the earlier mathematical models which were introduced in order to explain this particular effect. They were reasonable, but with the asymptotically correct theory, you see that a much more better result is obtained. Again, this particular experiment was done on specimens which had a pre-twist, and therefore you see the result for the one with the pre-twist, which considers in the asymptotical theory the pre-twist, is much better than the one which does not consider the pre-twist. And as you increase the pre-twist angle, this difference you will see becomes farther and farther. This was a fairly small value of pre-twist, and for that itself you see there is quite a difference, because the pre-twist plays quite an important role in the trapeze effect. In particular, it not only changes the nonlinear behavior, but the linear part of the nonlinear behavior is also changed by the presence or absence of pre-twist. So that's the reason why that is important as well. So what actually happens here is you're basically having a non-zero value of the axial force. In all these cases, F's represent the force and M's represent the moments. Again, both are internal, or in other words, they are the reactive behavior at any given reference cross-section. And the components, of course, 1, 2, 3 represent the components along the respective directions of B1, B2, B3, as we have been discussing earlier. So F1 is basically nothing but an axial force, and theta 1 is a rotation about the x1 direction, which basically means that it is a twist. So an non-zero F1 results in a non-zero theta 1. So that is basically the extension twist coupling. And of course the fact that it is nonlinear, as is very clear from this particular example plot. Now what happens really here is an out of plane warping, whereas the previous example was an in-plane warping, where you saw that the circular cross-section became ovalized, and in other words the shape of the cross-section changed. In other words, the W2 and W3 warping components were non-zero primarily. Though W1 could have been there to a small extent there as well, but the primary or leading terms were W2 and W3, whereas here it is basically W1, or in other words out of plane warping. You know that torsion of non-circular cross sections will cause warping. Here of course you are applying an extension load, and that is resulting in a twist, and which in turn is resulting in an out of plane warping. And that out of plane warping predominantly exhibits itself as what is known as a local rotation, and that particular rotation, if you see, is basically in this thin strip. If you take an element like this, which is basically perpendicular to the plane of the strip, if you think of it as a plate, and that particular normal line element basically rotates like this, and it rotates differently at different locations along the width of the beam, and that is what is basically causing such a large nonlinear coupling between the extension and twist. That is basically this difference that we are talking about between a linear theory and a nonlinear theory. Why it happens is primarily because of that so-called local rotation, as opposed to a rotation of the cross-section itself in any of these directions. We are talking about a local rotation of a line element which is perpendicular to the plane of the strip. So that local rotation is not small. It's proportional to the twist per unit length and to the distance of the line element from the center. So the farther it is from the center, the more the rotation it is, and the more the twist per unit length, the more that particular rotation that we are talking about. So this local rotation is what causes the extension twist relationship to become nonlinear. Now, there are two cases that we can consider. First, the tensile load. The tensile load, which is what is most common in many of the engineering structures that, whose examples we discussed. Now, if F1 is greater than 0, it's, as we discussed in the simple situations, the effective torsional stiffness increases, and obviously when the torsional stiffness increases, the frequency associated with it, the natural frequency in torsion, will also increase. If it's a rotating beam, the rotating beam, there is an axial load, whereas in the non-rotating beam there is no axial load because there is no centrifugal force there, unless you are actually applying physical force which is axial. So a difference between a beam, the same beam, which is in one situation rotating and the other situation is not rotating, is that one primary difference is that torsional frequencies, the natural frequency in torsion is basically larger for the rotating beam as compared to the non-rotating beam, and the reason is this. Next, if you look at the axial load being negative, obviously it is compression. You're all familiar with buckling, which is flexural, but there can be another type of buckling which is torsional. Typically happens with cross sections which are torsionally soft. In other words, the torsional stiffness is much lower compared to the bending stiffness. So it's the weaker link, and therefore the instability is of course similar. In both situations it is unstable, whether it's flexural buckling or torsional buckling, but just that because it's torsionally softer compared to flexurally, it can basically undergo a large twist at a particular value of the negative axial load. So that's, and that if you want to analyze, if you want to determine the torsional buckling and or the post-buckling behavior in terms of how the geometry changes as you continue to increase, let's say, the axial load and or other loads which might be combined with the axial load, then unless and until you have a nonlinear theory which takes care of this, you will not be able to predict all of that accurately. In fact, you will be way off from what is observed in experiments. So this is as far as the physical description of the trapeze effect is concerned. Do any of you have any doubts on this? Okay, if you have any, we'll come back to it later. Next, the trapeze, again you see this particular circus where many trapeze artists are demonstrating what I was actually talking to you about earlier. The trapeze and other nonlinear effects of same order, modeled based on VAM, implemented in two ways, and we will take a look at both of these ways. One is basically as closed form analytical solutions, and examples of those are listed in terms of the authors as well as the year of publication. And then the other one is basically as a finite element code. So in other words, you develop a theory, and the same theory and or modified forms of it can either be available as closed form analytical solutions if the geometries are simpler, or as finite element codes for more generic geometries, especially useful when the geometries are more complex and or the material distributions are much more complex. So the finite element code which is associated with an asymptotically correct theory is what is abbreviated as VABS, Variational Asymptotic Beam Section Analysis Software, and that was initially obtained or written by Sesnick, but right now I'm focusing on the inclusion of the nonlinear effects such as trapeze effect, and that was done by Popescu, and of course there have been many other revised versions of that by various other authors. But in all such situations you will see that only up to cubic terms are included in the software, whereas in the closed form analytical solutions you have all the way up to quartic solutions for not only thin rectangular cross sections but also for thin walled open cross sections like eye sections, channel sections, hat sections, the cruciforms that I talked about, etc. So how does it look like? To give you a sample of that, for example, for strips, that is basically thin rectangular cross sections, if you didn't have any nonlinearity in the cross section, the one-dimensional strain energy density would have just contained this first term here alone, where you have a 4x4 matrix SN, which is what we've been talking about as the S11 bar to S44 bar earlier. And each one of those terms are associated with a gamma 11 bar, kappa 1 bar, kappa 2 bar, and kappa 3 bar. So basically, you have the extensional strain, the twist per unit length, and the two bending curvatures, and all the elements of SL are constants. In other words, you have a linear cross-sectional theory. In other words, the relationship between axial force and gamma 11, the torque per unit length and the twist per unit length, and the bending moments and the bending curvature are all linear in such a situation. But what makes it nonlinear are these two additional terms, and where again the same symbol epsilon L is used for this column vector of 4 one-dimensional strains. Remember that all of these are one-dimensional strains in the sense that they are all functions of x1 alone. And then you have epsilon n, which is basically consisting of not the entire set of the quadratic components, but basically a few which are asymptotically relevant are only included there. Kappa 1 squared, kappa 2 squared, for example, kappa 3 squared is not there. The reason is, for example, of course, all these are results derived from the asymptotical theory, but a physical explanation for why kappa 3 squared, for example, is not there is that the energy contribution of that is much higher order, because of the fact that in a thin strip like this, you can see that the bending like this is what is called results in a curvature of kappa 2, whereas a bending like this results in curvature kappa 3. Now kappa 2 can be much larger compared to kappa 3 because it is much stiffer in bending in this particular direction, and therefore the contribution of kappa 3 squared terms will be much higher order compared to the contribution of kappa 2 squared, and that's how automatically the variational asymptotic method leaves out that term. Similarly, many other quadratic of the same strain as well as combination terms are also left out. In spite of that, again you will have coupling, as you see, between epsilon L and epsilon n, which results in a whole lot of cubic terms, which are all included in the finite element code as well. And then there are some which are quartic as well, as you see here, which are specific to strip-like cross sections, which you don't see, for example, to a large extent in thin-walled open cross sections, where you see terms which are basically going to be the square of each one of these terms as well as coupling between themselves, which are all going to be quartic in nature, and that's going to contribute a whole lot more nonlinear terms. And this is one way of expressing this particular relationship. You can still go back and express it just as this first term, but with this matrix no longer constants consisting of constant elements, but instead of functions. Okay, so in other words, you can take the derivative of this u1t twice with respect to each one of these strains, gamma 11, kappa 1, kappa 2, kappa 3. The first time you take a derivative, you will get the forces and the moments. The second, this axial force, the bending moment, the torque and the two bending moments. The second time you take a derivative with respect to each one of these, not only like dou squared u1d divided by dou gamma 1 squared, but also combinations dou squared u1d by dou gamma 1 1, dou kappa 1, etc., then you basically can populate that particular matrix SL in an equivalent form, and then you will basically see that those terms will become functions of gamma 1 1, kappa 1, kappa 2, kappa 3, in particular kappa 1 and kappa 2 more, because they are the large quantities as far as strips are concerned, because it is torsionally soft. At the same time, it is also soft in bending in one of these directions. So these are the two large quantities in this vector. Of course, they are dimensionally different. This is a non-dimensional quantity, whereas these are per unit length. But if you appropriately non-dimensionalize all of them, you would understand what I'm talking about. But the primary comparison is between these three curvatures that we're talking about, the torsional curvature and the two bending curvatures, and you see that in this particular situation, you can have large values for these compared to this, and that's what results in an equivalent SL bar. If you want to leave out these terms, I express it as just this term, to have to be primarily functions of kappa 1 and kappa 2. And then you have, that's for strips. Then if you look at open cross-section beams, like any generic open cross-section beams, eye section, hat section, etc., in all situations where you do have thin walls, but if you take any two orthogonal directions in the cross-section, the dimensions are, they may be numerically different, but they are not order of magnitude different. They're all of the same order of magnitude. In such a situation, you will end up with a matrix like this, much simpler if you compare to this as far as nonlinearities are concerned, because there are a whole lot more nonlinear terms here compared to here, where the only nonlinear term that you see is kappa 1 squared. It's very easy to see. You just take this strip, or probably just take two strips like this, and let's say we combine these strips like this to form an angle section, for example. You basically see that now, whereas in this case you had this curvature being much larger compared to this curvature, once this comes in here, you see that this bending stiffness is now going to be provided by this component, whereas this bending stiffness is primarily going to be provided by this component, and therefore you have in both these directions the bending curvatures are of the same order of magnitude. One is not much larger than the other, but still you will have the torsional softness because it is an open cross section, and the way open cross sections react to a torque is through a shear flow which tends to turn around itself in each of the walls. Unlike in a circular cross section like this, where the shear flow can go all around, so that the moment arm that you have now is basically the radius of the cross section itself. Whereas in a situation like this, when I apply a torque, the way this reacts to the torsion is through a shear flow which comes like this, turns around itself and comes like this. In other words, in each one of these, the moment arm is of the order of magnitude of the thickness rather than of the cross-sectional dimension, and that's the reason why you have it torsionally soft, and therefore the torsional stiffness is low, and therefore kappa 1 can be much larger compared to kappa 2 and kappa 3, and therefore a nonlinearity associated with kappa 1 is present, whereas the other nonlinearities have all disappeared in a open cross section when you go from a strip to an open cross section. So this is again something which is strange to a lot of beginners, that a strip which looks so much simpler in terms of the geometry is so much more complex in terms of the nonlinear behavior, whereas any arbitrary open cross section which is a little one step more complex compared to the strips in terms of the geometry is actually very simple as far as the nonlinear terms are concerned. But you get an additional term which was not present here, which is basically this particular kappa 1 prime term, which comes because of the restrained warping effect, which is a higher order effect here. Not that it is not present here, but it is not as important as these two terms. It would come as a much higher order term, whereas here it comes out as a term which is of equal significance in terms of asymptotical correctness, equal significance as the nonlinear term. So that's the reason why you see that there is an additional complication which results here, but this complication is something which makes life more difficult for the 1D analysis rather than for the cross-sectional analysis itself, where you basically have now this 6x6 matrix which is associated with the open sections. So any doubts on this so far? Okay, let's go. So now, as far as the finite element code is concerned, as I said, the cross-sectional nonlinearity was first introduced by Popescu in 1999, and then you basically can modify the three types of constitutive laws that we have been talking about by either or not adding this term depending upon the particular cross-section where nonlinearity is important or not, because we already discussed for which types of cross-sections the nonlinearity is important. For thin-walled open sections, some kind of nonlinearity is important. For thin-walled closed cross-section, some other type of nonlinearity is important. For strips, again, a different set of nonlinearities are important. So basically, you have this one-dimensional strain energy density or energy per unit length of the beam, which is modified to include the trapeze effect terms, which you see in the last line here, calculated by WAPS, now contains up to cubic terms, as I already mentioned, in the 1D generalized strains, and the general forms are basically without the nonlinearity 3, that is the basic where you have all the one-dimensional strains with bars, because you're basically setting gamma 1,2 and gamma 1,3 to be 0, or in other words, basically letting the warping to take care of them. So in such a situation, you have just a 4x4 matrix there with 4 1D strains for all the classes, and that's something which is valid for all classes. In other words, whether it is a solid cross section, whether it is a thin-walled open cross section, whether it is a strip, whether it is let's say thin-walled open cross section. In all such situations, the classical theory of the zeroth order approximation is basically this. That's after which you start refining it, and two sets of refinements that we have already looked at. One is where you have thin-walled open cross-section, and therefore you basically have restrained warping coming in, that is kappa 1 prime is coming in. And the other situation where you have short stubby beams, basically solid cross-sections and or closed cross-sections. Then in such situations you want to explicitly bring out gamma 1 to gamma 1,3 because you're focused on certain kinds of behaviors. For example, in terms of high frequency dynamic behavior, in such situations you basically look for this 6x6. But in each one of these three, if the nonlinearity becomes important, then you basically add this set. Or in other words, in a finite element kind of an implementation in the software, you can set a flag, and you can either set that flag to be true or false depending upon whether you want the nonlinear terms to be included or not included, depending upon the specific kind of configuration that you are looking at. So next, the cross-sectional nonlinearity in WAPS, as I said, is cubic, because if you actually look at that term, you have these two contributing quadratic terms, whereas each one of these are having linear terms, A, B, C and D being constants. Therefore, you see that the total contribution to the energy will be a cubic term. So A, B, C and D are 4x4 matrices. Each one of them have a whole lot of zeros. They're not fully populated matrices. So it's very easy to see that, because kappa 1 and kappa 2 will be the primary contributions if it's a strip-like cross-section, and if it is a open cross-section, then primarily B will be the major contribution. But of course, because you have a kappa 1 squared coming from here and the extension twist is a trapeze effect, you might have certain A terms coming in as well. So all cubic terms are not, as I said, equally significant. In fact, all cubic terms typically small for most of the beams that are of practical interest. But for certain beams, a few terms become important, and some examples are the open cross-section beam, where the trapeze effect is important, and there the torsional rigidity S44. Remember that in the 4x4 classical matrix that we have, this S44, sorry, I think it should be S22 if it's in the classical matrix, but I think this is for the with the transverse shear, where you have gamma 1,1, gamma 1,2, gamma 1,3, and then kappa 1. So the kappa 1 is the fourth in the order, and therefore you're talking about S44 there. Okay. Whereas if it were the barred quantities, you would be talking about S bar 22. So the torsional rigidity for open cross sections is small, and so in other words, S44 is small. In other words, the nonlinearity associated with kappa 1 become important. A22, for example, is the 2 term, so it multiplies kappa 1 squared with gamma 1 1. So it's an extension twist kind of a coupling. Again, B12, if you look at the 1 2 term is gamma 1 1 kappa 1, and that's multiplied by kappa 1. So again, it's a gamma 1 1 kappa 1 squared kind of a term. So those would be typically large for most open cross sections. So other terms formally would be of the same order. Of course, there will be a whole lot of zeros, but the non-zero terms which are there would also be there. In other words, if you look at only the variables involved and look at their orders of magnitude, it might look that they are of the same order of magnitude as the contribution to the energy from A22 and B12, but they might have numerical coefficients which turn out to be much smaller, and therefore in reality they are not as significant as A22 and B12. And this is something which typically happens with the asymptotically correct results, that you might sometimes be carrying on some terms which are numerically small, but just that they are qualitatively their orders of magnitude are large. But it doesn't matter, because only problem will come is if you leave out certain terms which are of the same order of magnitude that you wanted to consider. On the other hand, whether you have or don't have higher order terms which you are anyway not interested in, it really doesn't matter, because the order of magnitude is correct only up to the order that you are trying to derive the theory for. So, including small terms does not affect asymptotical exactness in the full expression. So, in other words, all the other A, B, C, D terms other than A22 and B12, for example, for an open cross section, even though they might be there and contributing small numerical values, it really doesn't affect the theory as a whole and the overall results as well, except for certain small numerical errors. So when and why certain terms are important leads to the classification of beams on a cross-sectional basis. So and now the question is, we have 6 different cross-sectional stiffness results, or the results for the energy per unit length of the beam that we saw in the previous slide. One is basically the 4x4 classical theory, then you have the 5x5 with the kappa 1 prime or the restrained warping, and then you have the next one which is basically including the transverse shear, and each one of these 3 once again combined with or without the nonlinear terms that you see over here. So you have a set of 3 into 2, 6 different theories. Now which theory to be applied when is basically what leads to a classification of cross sections, which we will do in today's class. Once we are done with that, it will become very clear which theory can be used when. But of course, while you are deriving the theory, you already know a priori which kind of cross section that you are deriving the theory for, so it automatically one of those 6 only will come out at any given order of magnitude that you are interested in. It's only when you already have these theories and rather their end results in place, and you want to apply it to a new problem, then you want to see which of these theories is valid for that particular beam. Then this kind of classification that we are going to do as far as cross sections are concerned will become relevant, because that will help us to choose one of those 6 theories to be applied to that beam for the kind of results that we are interested in. So what we are going to do now is beam classification based on asymptotics, or you can think of it in alternate ways as the based on the cross-section type or based on the constitutive law. When it's based on the constitutive law, we are talking about those 6 constitutive laws that we already listed. We are talking about the cross-sectional type. We are talking about whether it is thin-walled open cross-section, or whether it is thin-walled solid cross-section, regular cross-section, or a strip-like cross-section, etc. And we are talking about asymptotics. We are basically talking about up to what order of magnitude in the small terms identified are you going forward in terms of deriving the theory. But eventually that classification, irrespective of whether you do with respect to any of these, turns out to be the same, because all the theories are derived based on the asymptotics, and the asymptotic results are different depending upon your initial cross-sectional type that you chose, or in other words, the presence of certain small parameters in the cross-section or not. For example, if you start with a cross-section which is, let's say, a square cross-section, solid square cross-section, you know that the order of magnitude terms, there is no small parameter within the cross-section geometry itself. In other words, there is all the dimensions that you take within the cross section for a square cross section or a solid circular cross section for that matter are the same. So therefore there is no small parameter associated with it, and the kind of asymptotic theory that will result will be unique to that kind of or that class of beams. On the other hand, when you do it for a strip-like beam like this, you have not only the regular cross-sectional dimension divided by length small parameter, but you also now have within the cross-section itself another small parameter, which is the thickness divided by the width, and that will result in a different set of asymptotic theories, and therefore you know that those theories are applicable for this kind of beams, the strip-like beams. So in that sense, irrespective of what you're thinking about, if for the person who is deriving the theories, this makes more sense. Whereas for the person who is applying the theory, this makes more sense. And for the person who is applying, let's say, the finite element solutions, where he has to choose which particular model for that particular thing, then the constitutive law has to be appropriately chosen. But one is equivalent to the other. So we want to go ahead and classify beams based on the asymptotics. So some different types of cross sections which are available, for example, in commercial software are basically illustrated over here, and these are also the kind of things that you are commonly observing in a lot of engineering structures, and these are all the kinds of things that we want to be able to model using an asymptotically correct theory derived using VAM as well. So how should, first of all, beams be classed? There are many ways in which you can classify beams, and the beams have been analyzed over a long period of time, and different people have classified it in different ways for rightful reasons, of course. But the way we will classify it will be based on the asymptotics, as we already discussed. So we discussed 6 one-dimensional constitutive models which result out of the application of VAM. The first and the second model are a classical model, which is the 4x4 model, with and without the nonlinear effects, that is the cubic terms that we discussed in the previous and the slides before that as well. The third and fourth constitutive models are the generalized Timoshenko models, where you will explicitly bring in gamma 1,2 and gamma 1,3, which are the transverse shear 1D strain measures. And so in addition to the 4 that you already have, namely gamma 1, kappa 2 and kappa 3. So you have a 6x6 matrix, again with and without the nonlinear effects depending upon a particular cross-section geometry. And finally you have set 5 and 6, which basically are generalized Vlasov theories. By Vlasov we mean the restrained warping effect, where kappa 1 prime comes into the constitutive law, the 1D constitutive law, and contributes to the energy per unit length of the beam. Once again, it can be exercised with or without the nonlinear effect. So this is the these are the 6 choices that you have for the application of an asymptotically correct theory to a new candidate beam. So when to use which model is the question that we would like to answer, and this is answered by a lot of recent work which has been done in the variational asymptotic community, which has led to the beam classification that we are going to discuss in the next few slides. So the beam classification, as I said, will be based on the asymptotic results, and once we go through this, it will be very clear that because of this classification, one is of course the utility of the classification is you will be able to choose which model of amongst these 6 to use for a new candidate beam. But even the classification by itself, even without looking into an application point of view, will be educative and quite practical, as you will observe shortly. So let's go ahead and classify the beams. And again, this classification is designed to be a mnemonic. In other words, the name given to each of these classes of beams has a particular significance, as you will see very shortly, and each one of those will be mnemonic. In other words, it will be related to the kind of beam that it represents. So the first class that we will be talking about are the class T beams, where the T stands for thin. So thin-walled open cross sections is what we will restrict that class to. So an example of that is an I cross section beam, where the flange width and the web height are basically of the same order of magnitude. B and A are of the same order of magnitude, but still the thicknesses, let us say, of the flange and the web, which of course can all be different from each other, but are of an order of magnitude higher compared to B and A. In other words, H is small, very small compared to B and A. So these are the thin-walled open cross sections. Again, I section is illustrative, but there are many other such beams like channel, hat section, Z section, etc., cruciform. The next class is the class S beam, where the letter S stands for the word strip. So they are strip-like beams, which is not restricted to thin rectangular cross sections alone, but also any other thin cross sections, such that the geometry is such that if you take two directions which are orthogonal, you basically see that the dimensions of the structure are very different from each other in terms of an order of magnitude. So if you have a thin airfoil cross section like this, even that can be classified as a strip-like cross section, or in other words, what we call as class SB. So of course we have the thin rectangular cross section, and each one of these situations, it can have an initial twist, it can have an initial curvature, etc. It is irrespective of that. What we are focused on is just the cross-sectional geometry now, used as a basis of classification, and which in turn also turns out to be equivalent, as I said, to the asymptotic theories for each one of them being different. The third class is the rest of the beams. What is not included in the first two classes, which are neither thin-walled open cross-section nor strip-like beams, or what we call as R for rest or R for remaining, or what in some literature is called as regular beams. Okay, so this of course includes solid cross sections like this, a rectangular cross section with or without a chamfer, for example. Then you have very thick airfoil cross sections like these, or you could have the kind of cross section that we were talking about for the brazier effect. But again, there is a small diversion there. Within the R class, you can have two types. One where the brazier effect is important, and the other where the brazier effect is not at all important, as you would see in something like this. For example, if you have a bending moment applied to a beam with a cross section like this, then you would see that the flattening effect that you would have would be negligible, and therefore the reduction in bending stiffness would be negligible, and therefore the moment curvature relationship would be predominantly linear. The nonlinear effect would be very, very minimal. But basically, these are the three major classifications that you have: thin-walled open cross-sections, strip-like, and the rest of the cross-sections, which primarily include solid cross-sections and thick closed cross-sections. Now, there is a primary difference which comes in terms of the kind of behavior. Right now I'm leaving out brazier, as I said, because that involves a further classification or a second level of classification within the R class beams, for example. To some extent, even S class beams exhibit the brazier effect, the nonlinear bending effect. For example, you know that this bending curvature is very large, and therefore nonlinearities can be associated with this bending as well, which are predominantly a brazier-like effect, which can be observed with S-class beams as well. Leaving that aside, let us focus just on the torsional behaviors. If you look at the torsional behaviors, two major non-classical effects are there. One is the generalized Blasov, which is basically the restrained warping effect, because of which kappa 1 prime starts contributing to the strain energy, and the trapeze effect, where the nonlinearity in the kappa 1 becomes important. In other words, more than quadratic terms contribute for the 1D strain energy density. So now these are the three classes of beams: class R, class S, and class T. If you look at class R, that is the simplest as far as torsion is concerned, because the torsional stiffness for these beams are fairly large, and therefore the torsional curvature, or what we call as the twist per unit length, is pretty small. It's a higher order term, and therefore neither Blasov or kappa 1 prime kind of effect nor kappa 1 higher power effect will be important there. And the reason is all the kappa of such beams, or class R beams, are of the same order of magnitude. So in other words, a bending moment like this, a bending moment like this, The stiffnesses, of course, are going to be different. EI2 and EI3 are numerically different, but they are not an order of magnitude different from each other. They are of the same order of magnitude. Similarly, the torsional stiffness is also of the same order of magnitude, and therefore the curvatures which are associated with it, which are kappa 1, kappa 2 and kappa 3, are all of the same order of magnitude, and therefore neither of these becomes important. Next we go look at the S-class beams, and the generalized Vlasov doesn't affect there, the restrained warping doesn't affect that. That is not very clear right now in terms of a physical explanation, but when you see the mathematical derivation, you will see that the kappa 1 prime does become important, but it is not of the same importance as the trapeze effect. In other words, these are much more critical than this, and therefore this will come out as a higher order refinement, which for most engineering applications is not necessary, and therefore you see that the generalized Vlasov is not very significant there. Again, the example that I gave for that generalized Vlasov, where I showed you an I section with the forces going in and out at the four ends of the flanges, so that the net resultant force and net resultant moment is zero, but you still have an effect. Something like that cannot be duplicated in a strip-like beam, for example. In other words, you see, you can think of examples which can describe to you physically why the restrained warping doesn't play as important a role in S-class beams as it does in the T-class beams. So in the T-class beams, as far as torsion is concerned, become the most complex because they have nonlinear effects and they have the restrained warping effects. So in other words, the 1D modeling is going to be complicated because they have more boundary conditions than you would otherwise be associated with it because of the presence of kappa 1 prime in your 1D theory. So in the case of S-class beams, one bending measure is smaller than the other kappa I. So basically you see that kappa 1 is large, kappa 2 is large, but kappa 3 is small. So one bending measure is smaller than the other kappa I. In other words, kappa 3 is basically smaller compared to kappa 1 and kappa 2. On the other hand, here torsion larger than either of the bending measures. So if you have an open cross sections like this, so here you see that the bending this way, it offers substantial resistance. Again, in this way it may not be as high as in this case, but still it has a reasonable bending resistance, but the torsional resistance is very low. In other words, kappa 1 is much larger compared to kappa 2 and or kappa 3. So that's the reason why you see in that situation, the T-class beams, you have both the Vlasov and the trapeze effects coming into picture. So now we'll go into each one of them a little more detail. So class T beams, which are basically thin-walled open cross-section beams. An example is this. So this is again very illustrative of some standard procedures which some of you might already be exposed to, by which I sections are made. Of course, this is not the only way, but many situations it is made in this particular way, where you can see that it is the same ply which goes around and comes here like this, and it is bent around itself. And here you in the web you see only 090. In other words, it's a cross ply kind of a laminate. So that cross ply laminate is bent around itself, and basically you end up with a situation like this. But in such a situation, you should also take into effect the complication that in the same ply, in some parts you will have 0 degree, and some parts you can have a 90 degree as well. So situation like that. And then over and above that, in this particular case, you see there is a 0 degree layup, and then there is an angle ply which is also placed, two sets of angle plies which are placed over that. So this is one way of constructing an I section. There are many other ways of constructing it, but irrespective of the way it is constructed, what is important for us as far as the asymptotic theory is concerned is that the thickness of the flange, the thickness of the web are both an order of magnitude higher compared to the overall height of the web and the width of the flange. Okay, so applications, of course, in civilian structures and built-up plate girders where you have support beams for buildings. So that's a very standard case where I sections are used, and it could be other open sections as well. Again, for bridges, heavy machinery in mechanical engineering, Again, in aircraft, you have these stringers, which are the stiffeners in the wings, and then you could have spars. Again, you could have them in the fuselage as well. Then the helicopter bearingless rotor flex beams. So once again, it's a very standard example of class T beams. Of course, there are some class S beams also amongst the helicopter bearing rotor flex beams, especially for tail rotors. Then the wall thickness is what we will call as order of magnitude H, which is basically this and this. Again, to repeat, they can be numerically different. This flange thickness, and this web thickness can be 3 different numerical values, but they're all of the same order of magnitude. So that's what is important here. That's what we call as H. Okay, then the main characteristic length of the cross section is again A. So once again, this is A and this is B numerically, but A and B are of the same order of magnitude, which we call as order of magnitude A. Then the maximum strain before material failure is of the order epsilon, and this could be any one of the 6 components of strain and anywhere in the cross section and along the length of the beam, and if it's a dynamics problem, over the time interval of consideration for the dynamics of the beam. Next, you consider the torque M1, which is, in other words, you're basically for the I section you're applying a torque. So the what results because of that is a shear flow. It is through the shear flow that the beam resists the applied torque. So the resisting shear flow will have to turn around at each wall edge. So in other words, you're applying a torque here, so that has to be at that's at the end of the beam. That's the load that you're applying is the torque at the end of the beam. So somewhere you cut along the beam on that cross section, that torque has to be resisted by means of a shear flow, and because it's not a closed cross section but an open cross section, there has to be a shear flow which is in the opposite direction. So there will be a shear flow which goes around like this and comes around like this. Okay, and if you look at each component like here, the moment arm that shear flow has is basically because of a couple that is over there, and so the moment arm is of the order of magnitude of the thickness. Again, here the shear flow at the 2 edges basically going like this, and that's basically again the moment arm is of the order of magnitude of the thickness. So that's what creates the issue here in terms of lower torsional stiffnesses, larger kappa 1 or twist per unit length. So once we have this M1, the resulting shear flow turns around at each edge wall, which implies that the maximum strain induced is of the order of H times kappa 1. So basically remember that the strain that comes out because of a torque is basically a shear strain, and that shear strain is proportional to the twist per unit length, and it's proportional to the moment arm, which is of the order of magnitude H as we just discussed, and therefore the strain which is induced is of the order of H times kappa 1. This is of course something which we can intuitively see or from the kind of knowledge that we have gained, but we can and will derive the actual expressions for the strain, and there we will actually show that it indeed is of this order of magnitude. So for now, you just take it for granted either from your intuition or from my explanation here that the maximum strain induced is of the order of H times kappa 1 because it is proportional to the moment arm and it's proportional to how much of twist per unit length the cross section is undergoing. So because of that fact, the maximum twisting curvature kappa 1, its order of magnitude can be established because the maximum strain can go only up to the material failure, which is of the order of epsilon as we already discussed over here. So therefore, epsilon is of the order of H kappa 1. In other words, kappa 1 max can be at the most order of epsilon divided by H. Of course, it can be 0, but at the most, at the failure of the material, it can reach epsilon by H. So that is the order of magnitude of the twisting curvature. Now consider the bending moment M alpha, that is M2 and M3. So instead of the torque M1, let us say we apply either M2 or M3 as a bending moment to that same I section which we were considering. The resulting axial strain is now proportional to the distance from the neutral axis. Unlike here where it is proportional to the moment arm of that shear flow, Here it is proportional to the distance from the neutral axis. Now that distance from the neutral axis could be either a by 2 or b by 2, which are of the order of a in terms of orders of magnitude. So in other words, the maximum bending strain which is introduced, which is of course an axial strain, because of the bending moment you are going to have an axial strain, partly compressive and partly tensile, but irrespective of whether it's tensile or compressive, in the outermost fibers the maximum strain that you will have will be proportional to the A, and it will be proportional to the bending curvature, right? So that's something which comes purely from the geometry of the bending, which is basically the curve that you have and therefore the behavior at each fiber along the cross section. So you basically have the maximum strain of the order of A kappa alpha. Once again, that cannot exceed the material failure limit, and therefore you can estimate now the order of magnitude of kappa alpha, that is both kappa 2 and kappa 3. Here the Greek subscript alpha refers to the smaller dimensions in the beam. The larger dimension is 1, which is along the length of the beam. Alpha, beta, gamma, whatever Greek subscripts that I might use, unless and otherwise I specified, can vary between 2 and 3. That is within the cross-sectional coordinates, that is x2 and x3. So here I can estimate kappa 2 and kappa 3 because this is of the order of epsilon. Therefore, the maximum bending curvature that can be reached at failure is basically order of epsilon divided by A, right, in both the directions, kappa 2 and kappa 3. Now if you compare these two, the maximum twisting curvature can be epsilon by h, whereas the maximum bending curvature can be epsilon by A. And h and A are quite different from each other in terms of order of magnitude. H is much smaller compared to A. So h is very small compared to A, means that the twisting curvature will be much larger compared to the bending curvature in general, and therefore class T beams torsionally soft, that is your torsional stiffness Gj will be small compared to Ei alpha in the case of isotropic beam, stating the same thing in the case of composite beam or even an isotropic beam in a more general notation that we have been introducing, the 4x4 matrix, where the second row and column are with respect to kappa 1 and the last, third and fourth are with respect to basically the bending. So you'll see that S bar 22 is very small compared to S bar 33 or S bar 44, right? So that's basically the conclusion that we reach here as far as the T class beams are concerned. So let's do a similar thing as far as the class S beams are concerned. So class S beam, once again, this is strip-like configuration. Now we have a small parameter associated with the cross section, which is the thickness divided by the width. Again, we are introducing x1 along the length, x2 and x3 are along the cross section. It can or cannot be with initial twist and curvature. When initial twist and or curvature are there, your B2 and B3 will be functions of x1. So that's basically written over there. Of course, when there is initial curvature, B1 will also be function of x1 in general. So applications for strip-like beams would be high aspect ratio thin airfoil wings, okay, and helicopter blades, especially tail rotor blades, flex beams. Now, like class T beams, class S beams also have two different cross-sectional length scales. One is order H and the order B, different from each other. Next, class S beam is soft in torsion and also bending in one direction. Already we have illustrated that bending in this direction is soft. So one bending stiffness, which is basically the bending stiffness about this direction, is much larger compared to the torsional stiffness and the other bending stiffness. So now if the strip dimensions, as in this case, are length L, breadth B and height H, L, B and H, with L being much larger than B and B being much larger than H. Of course, this particular thing is necessary for it to be classified as a beam. Otherwise, you would have to treat it as a plate, where L and B are of the same order of magnitude and H is much smaller than that. But in a situation where you have this, you can either treat it as a beam or as a plate. Both possibilities are there. But with initial twist and curvature, it would be a shell rather than a plane. Now, strain induced by torsion is of the order h times kappa 1. Once again, for the same reason, if I apply a torque, it is going to be, when I cut somewhere here, the shear flow that is going to be there is going to go around itself. So the moment arm that shear flow will have will be in this, it will be going up and down. So basically it's the thickness. So once again you have it proportional to the twist per unit length and to the moment arm, which is h. Next, the strain induced by bending in the soft direction, that is basically in this particular direction, is proportional to the distance from the neutral axis, which is basically the order of magnitude is the thickness over there, and the corresponding bending curvature, because along the width direction we have introduced the coordinate x2, is kappa 2. So h times kappa 2. But the third direction is quite different. The strain induced by bending in the stiff direction, now the distance from the neutral axis is b by 2, which is of the order of magnitude b, and therefore it's of the order of magnitude of b times kappa 3, because now the bending is about the 3 direction, which is the thickness direction. So now you see that the strain order epsilon defines the upper limit in deformation for all these 3 cases, whether it is torsion, bending in the soft direction, or bending in the stiff direction. In all these cases, the maximum strain that it can reach is epsilon. Of course, you would see that this is actually shear, and therefore the failure in shear numerically might happen at a strain value which is different from the strain value at which bending failure or an axial strain failure might happen, but they are not order of magnitude different. That's what we are referring to by that term epsilon. So once we compare each one of these 3 with epsilon, it's very clear that kappa 1 and kappa 2, that is basically the twist per unit length and the curvature about the softer direction, are of the order of epsilon by h, whereas about the stiffer direction the bending curvature is going to be epsilon by b. Once again, the fact that h is very small compared to b basically means that kappa 1 and kappa 2 are much larger compared to kappa 3. Finally, look at the class R beams, which are the rest of the beams, neither thin-walled open cross-sections nor are they strip-like cross-sections. They are either solid cross-sections or thick-walled closed cross-sections. So examples of those would be beams with thick-walled closed cell and solid cross-sections. I already mentioned that. Class R, all beams that are neither class E nor class S. So no cross-sectional length scale effect in strains induced by both bending and twist. Of course, here I'm classifying the wall as far as the closed cell is concerned as thick-walled. Okay, if it is thin-walled, then the brazier effect will come into picture. So that's a special class that I want to leave out as an exception here. That's the reason why I put it as thick-walled here. So in such a situation where it is thick-walled or solid, you know that all kappa I will be of the same order of magnitude. We can use the same arguments that we used previously in order to show this. And of course the exception, which is basically the thin-walled closed cell cross-section with the large bending moments and therefore the large curvature, and therefore leading to a limit moment instability. So wall thickness slightly affects the order of strain induced by bending, and therefore in such situations where you have thin-walled closed cells, you can have the brazier effect, but it is not limited to thin-walled closed cross-sections alone. Even strips have somewhat similar behavior. So now once again we will look at kind of a summary of what we have seen. The non-classical nonlinearities in thin beams, that is basically the cross-sectional nonlinearities that we started out talking about. So with this slide I'll end today's class. So there are 3 classes of beams that we have: thin-walled open cross-sections, strip-like, and the rest, with an exception there of the beams which are basically thin-walled closed cross-sections. But in this particular slide I will take them into account as well. Now the beam shapes that we have are corresponding to those are open section, strip, and closed section. And then you have certain nonlinearities arising in each one of those. In this case only if it is thin-walled. If it is thick-walled and or solid, it will not be there. In the situation where it is thin-walled is what I am discussing right now. So the primary 3D sources of nonlinearity in the T class T is out of plane warping. Remember that everything there was associated with a twist in terms of 1D manifestation, and it's a twist which basically causes the out of plane warping. Again, this you're familiar from your more basic classes, because you know that any non-circular cross section when subjected to a torque results in out of plane warping. In other words, plane section doesn't remain plane anymore. So it is that which is basically what we are talking about, out of plane warping, or what we refer to as the W1 component. In the case of the closed cross section, it is the in-plane warping. Again, it was demonstrated for you in the Brazier effect, where a circular cross section became ovalized, or when you have a tensile load, for example, you can see that there is flattening because of the Poisson effect. So all those are in-plane warpings. But here we are focusing on the nonlinearities, and the nonlinearity example is the Brazier effect, and that is also governed by in-plane warping. In other words, W2 and W3 components. That is the warpings along the X2 and X3 directions. Now the strip is a combination of both. It has the in-plane warping from the closed cross section and the out-of-plane warping from the open cross section, and it acts somewhat like a borderline situation between these, because a strip you cannot really think of it either as a open cross section or as a closed cross section, even though it is thin. Okay, so that in that sense it is some kind of a borderline situation. Again, the in-plane warping was dominated by bending, as we showed in the Brazier effect, whereas the out-of-plane warping was dominated by twist. And when in the case of the strip, the in-plane and out-of-plane warping are due to a combination of twist and bending. So both come into picture over there. Once again, in terms of the 1D manifestation also, you can see that the strip acts like an interface between the open section and the closed section. Next, in terms of the nonlinear effect itself, the well-known non-classical effects are the trapeze and Vlasov effects. I'm not only talking about nonlinear effects, but non-classical, which are not accounted for in that 4x4 matrix. So in that sense, not only the nonlinear trapeze effect, but the linear but complex Vlasov effect because of the restrained warping. So that is there. On the other hand, in the closed cross section, the well-known non-classical effect is Brazier. And in the case of the strip, you have trapeze as well as Brazier-like effects. And in fact, these are just the well-known effects. In other words, things that have been historically observed over a very long period of time. But that doesn't mean that these are the only nonlinear effects. There can be many other types of nonlinear effects also. Okay. So, and once we see the actual results for the cross-sectional stiffness, for example, we will see where the nonlinearity exists and where they are different from either one of these already described or explained types of nonlinearities. Next again, so this is something which is irrelevant to this topic, so I'll just leave it aside. So again, these are further examples of the T-class beams for which we have closed form analytical solutions using the variation asymptotic method. Again, S-class beams or like this, or we can extend it theoretically to situations like the thin airfoil cross section that we talked about. Again, in R-class beams, we already have closed form analytical solutions for a circular cross section. We can do that for a box-like beam, where the box need not be rectangular but also tapered as well. So in such situations also it is possible to theoretically to get closed form analytical solutions. But in all other situations where it is much more complex geometry, we have VABs to do the asymptotically correct theory for us in terms of their results for the 1D stiffness as well as the recovery relations in terms of the warping. So with this I will end today's class, and in next class we'll talk a little more about VABs before we get on to the kinematics in terms of more rigorous equations.